5 minutes after every 1 hour. Is that okay? Or you want to have a bigger break of 10 minutes after 1 hour and a half? Yeah, you can make comment, colleagues and students on that side.
10 minutes will be fine, Prof.
After 1 hour and a half, yeah, okay.
Yes,
then you just remind me around 10:30 to stop, and then we'll have a break. And the arrangement is such that today it will be myself talking. If you have a question, you can interrupt me at any point. And tomorrow I'll provide you with some exercise that you'll take home. And exercise. Perhaps I'll show you also the resources, how to access them, and how to do those analysis that I'm going to present. Is my voice is okay? Everything is okay? Shall I proceed?
Okay. Yes, sir. We can hear you clearly.
Yeah, very good. Thank you. This is the outline. I have about 9 sections. First, I'll briefly talk about understanding drivers and the physical basis of climate change, which was perhaps touched to some extent yesterday. So I'll recap what has been said yesterday, and then the second item on this lecture series is the hydrological cycle. Again, you might have come across these topics. I know that I was told that you have a different background, but the way I'm going to deliver this is more generic and can be understood by any general person. And the third topic is impact of climate change here. And then generally, and then we talk about climate change impact on hydrological cycle. I don't know, my it's moving anyway. I don't have to touch my cursor. Do you see the cursor when I'm moving? You see the cursor on the screen?
Not yet. I cannot see the cursor. I'm not sure if the other colleagues can. We can just see the first slide on outline for the lectures.
Oh, okay. That means it's not working. Anyway, so I think you'll be able to follow. And then impact of climate change. Basically, I'll be narrating some of the observed climate change globally and in the region. And then we'll talk about climate change impact on the hydrological cycle. And we'll talk about climate extremes such as drought, floods, and other extremes, and their multidimensional nature. And the fifth topic. And the sixth one is impact of climate, or what I call hydrological extremes, on water quality. And then impact of climate change on water use sector, such as agriculture and vegetation condition. And then we'll talk about uncertainty in hydrological impacts. All the discussion that has been done in the previous 7th section has their own uncertainty. When you talk about impact of climate change on hydrological cycle, on different components of the climate system, we are not 100% sure. There are some uncertainties that arise due to different processes and assumptions. So we'll be talking about that and the uncertainty in hydrological impacts. And then the last one is focus on the SADC region, climate impact on water resource in the SADC region. And I'll try to cover all of it, but in case time doesn't allow that, this part will also be covered by Professor Marilla on Thursday, so you don't have to worry. Looking at the understanding the drivers of climate change and the physical basis, what we say climate change is basically about energy balance. As you know, the climate system consists of different spheres: atmosphere, the hydrosphere, the water component, and the biosphere, the vegetation, and the lithosphere, the solid earth, and so many others, including the we have also anthroposphere, the component of the human part, where human beings are interacting with climate. So they modify through this interaction climate. So there are about 6 components of climate system, and the climate is affected by interaction between them, between each other in different ways. So this interaction actually alters or changes the temperature of the atmosphere or land surface, because the temperature and temperature of the atmosphere or land surface is determined by the energy balance between incoming solar radiation. This is a kind of input to the climate system, and outgoing terrestrial radiation emitted by all components of the climate system. Those who are from different background may not know, but we know this is a basic concept. Any object with a temperature greater than 0 degree Kelvin emits radiation. That's not the radiation that we see visually. The radiation that we see visually is in the visible range, and there are other radiation components, such as infrared radiation emission due to temperature. Mostly we call it thermal emission, is in the infrared, and we cannot have vision for that kind of radiation, so we don't see them. But the fact that we don't see them doesn't mean that they don't exist. So they actually constitute major part of the energy coming even from the solar radiation. The energy coming from the solar radiation, most of it is in the visible range, and the remaining part are in the infrared radiation, ultraviolet radiation, even X-rays, gamma rays, and radio waves, so on. So climate is governed by the energy balance between what leaves the atmosphere, what leaves the climate system, and what comes into the climate system from the sun. So we have the so-called greenhouse gases, such as water vapor, methane, carbon dioxide, and so on. And these we call them greenhouse gases. These greenhouse gases actually help us to maintain that energy balance between what we gain from the sun and what we lose to the space. That is the part of the natural process. But in recent centuries, the last 115 years, there is this industrialization that led to excessive emission of carbon dioxide beyond what exists naturally, and excessive emission of methane and other greenhouse gases such as nitrous oxide. So because of industrial activity. So as a result, the amount of energy we lose to space through terrestrial radiation, through thermal radiation from the atmosphere, from the land surface, from the water body, is not going out to the space. They are captured by these greenhouse gases. So they are captured and returned back to the Earth's surface as a result, we start getting excess energy than what we are expected to have. So that means basically the atmosphere is getting energy from the sun. In addition, it's getting energy from itself as a result of greenhouse gases. So there is this excess energy in the climate system. This excess energy basically will increase the temperature of the climate system, whether it is land surface, whether it's atmospheric temperature, whether it's temperature of the water bodies, such as sea surface temperature, is going to increase. So what you see on these figures here, there are 4 panels. At the top, it's a globally averaged combined land and ocean surface temperature anomaly, starting from 1850 towards the beginning of the Industrial Revolution, and all the way to 2010. From these, you can clearly see that a steady increase in the global temperature since industrial times. And this increase is attributed to these greenhouse gases. In the lower panel, in the second lower panel, B, you see global average sea level change. So we said that this energy imbalance is going to affect all components of the climate system. So we are looking at the temperature of the sea, which constitutes a part of the hydrosphere. And in the third panel, actually, you can see the association between increase in these greenhouse gases and change in temperature. Change in temperature, you can see CO2, which is shown by green, and you can see methane, which is shown by more or less orange color, and you can see also nitric oxide, which is shown by somewhat red line. So all of them are steadily increasing from 1850 until recently. So that's why the global community is trying to limit the emission of these gases. So why we are really, I mean, the greenhouse gas effect existed even before the pre-industrial times, at the pre-industrial times, but what is different now is the excess in these greenhouse gases. You can see there is an Antarctic ice core records of CO2 concentration extending almost to 800,000 years, and that shows CO2 concentration was somewhere between 170 to 300 parts per million. Currently, we are at around 420 parts per million. So over 100 parts per million is attributed to industrial revolution, basically attributed to anthropogenic activity of the humankind. So the fluctuation in CO2 and temperature was also there before even industrialization started. It was there before 1850 throughout the history of Earth. And this change was basically related with what is known as orbital variation, Earth's orbital variation around the sun. It's called Milankovitch cycle. As a result of Milankovitch cycle, we used to have warm and cold period, glacial and interglacial period, every 100,000 years, So climate change was there, but the current climate change is part of interglacial period, the warm period, but we refer this period as super interglacial period because it is artificially created. It's not part of the natural process. That's why we are worried about climate change and a lot of activities going on in relation to climate change. So now, just for your information, how much each country has contributed to global warming or climate change can be measured basically by the greenhouse gas emission. For instance, what you see here is greenhouse gas emission in millions of tons. So the blue is the highest emission, and the green is the lowest emission. So as you can see, Africa stands out clearly out of the rest of the world because we are towards the lowest emission of greenhouse gases. So, but the fact that we are contributing less doesn't really shield us from climate change, because climate change is global. The atmosphere is connected. It's a system. Climate system is connected. There is no isolation. The system works in coordination. This is another example where you can clearly put CO2 increase and temperature change, and the change over time is in quite good agreement, where we have low emission of CO2. You can clearly see the temperature was low, and with as you go up to the red part, this is where we have a lot of emission, and correspondingly we see an increase in temperature. Now, to look at the contribution of other extreme event. Climate change is just one extreme event. We have also geophysical events, which is extreme, such as earthquake, tsunami, volcanic activity. We have other natural meteorological events, such as tropical storm, extratropical storm, convective storm, local storm. I think in Namibia you have this very often because you are at the coast. These are meteorological events, natural basically, but of course we'll see that climate change will also affect at least the strength, the intensity, and the frequency of occurrence of these extreme events. And you can see the hydrological events, flares, mass movement. This is part of, it's also affected by climate. And other climate events such as drought, forest fire, extreme temperature is shown by the orange color. And if you look at the time series of all these events, the geophysical events remains almost constant. As you can see, there's not much variation over time. There is a variability from one year to the other, but there is not any temporal trend. There is not any increase or decrease with time. So because it's occurring naturally. But when you look at other three meteorological events, hydrological events such as flood, mass movement, and basically landslides and so on, climatical event, you can see them increasing with time as a result of climate change. So I would like to summarize this topic of understanding climate change, drivers of climate change. Basically, we can categorize the cause of climate change into three components. On your right side, I guess there's natural causes here, natural causes, and then you have human-induced causes. You have also forcing, the natural forcing. So the natural causes are volcanic activity itself will change climate because as a result of volcanic activity, you get a lot of emission of aerosol into the atmosphere, and aerosols will interact with incoming solar radiation and also interact with outgoing long-wave radiation. So this interaction will either enhance the energy that we get or decrease the energy that we get, depending on the size of aerosols. So volcanic activity will affect climate change, but it's natural. It's not happening every time. As you see, it's a part of a geophysical event. If you have a volcanic eruption at one point, you may expect a cooling of the atmosphere, maybe for a period of 2 to 3 years, but after that, you will be back to normal. Change in solar output because of the solar activity, the energy we get from the sun is because of the chemical reaction going on. As you know, the sun is purely consists of hydrogen when it was born. Now, since its birth, this hydrogen is being converted to different forms of higher atoms, such as helium. So this conversion from smaller hydrogen atom to bigger ones will involve energy release. That's the energy that we get from the sun. So there is an activity in this case which enhances that kind of reaction. We call solar cycle. As a result of solar cycle, we may also get change in solar energy output from the sun. If there is a change in the solar energy output from the sun, climate is going to be affected because climate is about energy balance. It's all about energy balance, the balance between incoming energy and energy that leaves the climate system. So, so naturally, this will affect the climate system, but it occurs on a regular and on a long-term period. And even the volcanic activity, it occurs on episodically. It's not a regular event, and it lasts only for a short period of time. So it doesn't have much effect on the climate change. Human-induced effects, basically, are referring to burning of fossil fuels, conversion of forests and agricultural land due to urbanization, due to need for crops. You are converting, let's say, forest into agricultural land. That will change basically the land surface structure. The change in the land surface structure will affect the energy that is absorbed by the Earth system because you are going to change the reflectivity. We call it albedo of the Earth system as a result of change in the land cover. So this is human-induced causes, so it's part of anthropogenic activity. The forcers is long-lived substances such as greenhouse gases. These are part of the normal greenhouse gases. We have short-lived substances such as ozone, methane, black carbon, aerosol. These are methane lasts a few years. It's not very short. Short is compared to carbon dioxide. Carbon dioxide can last somewhere from 150 years to 1,000 years in the atmosphere once it's released. So you can imagine the effect of carbon dioxide is much stronger compared to most of the other greenhouse gases. So this is related with causes of climate change. The effects could be reflected on climate, warming, cooling, change on onset time of season. It could be impact on water availability. We'll talk shortly later on, for instance, about water quality itself. It's not only the amount of water which will be affected by climate, but also the water quality is going to be affected by climate. We'll talk that later on today or maybe tomorrow. Ocean acidification, it will affect also the agricultural output, livestock output, basically, which is related with food security. It will impact the tourism sector because it will impact the wildlife, for instance. So this is more part of socio-economic impact. And the energy sector will be impacted by climate because, for instance, hydropower plants is basically based on water, and the climate change will affect the amount of water that is available. So the effect is multifaceted and very complex. Actually, I cannot finish the list. These are just some of the studies. You can see that if you want to have detailed understanding of what I'm talking about, you can see the references here in front of each case. At different times, different people wrote about these cases. So that is all about the basic drivers of climate change and the physical basis of climate change. We can talk about this the whole day if you wish, but I think for you, you need a basic introduction, and as this, your focus is diverse, and you need this knowledge just for basic understanding. And now I'll move to topic number 2, which is the hydrological cycle. You see this 3 sketch here on this slide. We look at water balance in a basin, which includes evaporation, evapotranspiration, precipitation, and runoff, and water movement in the groundwater movement. So that consists of a balance of water in the basin. But as I said, climate system is not isolated. It's connected. It's not only just land surface and vegetation, as you can see here, but it also includes atmosphere. So if you look at the atmosphere alone, under panel B at the top, you see the water balance includes evapotranspiration, precipitation, and also water that exists in the atmosphere in the form of vapor. Yeah, no, water is a unique compound. I'll talk about it later. Compared to many other greenhouse gases, because you can find it in 3 forms: in liquid form, in gas form, and in solid form. And this process is continuously going on in the atmosphere. And during this process, there is a release of energy or uptake of energy. And this energy is the second major energy source, in addition to the solar energy that we get from the sun. So coming back to the hydrological cycle, we have these 3 components. And you can write an equation. The first equation, basically, water balance in the basin, which refers to part A, includes all the components I mentioned: precipitation, evaporation, runoff, and so on. And then you can talk about the water balance within the atmosphere alone, and that is the second equation, as you can see. And you can talk of the combined water balance, because you have the land surface, you have the vegetation on the land surface, you have atmosphere interacting with the land surface, the land surface interacting with the atmosphere, the biosphere, which is the vegetation interacting with all of them. So the energy, the water cycle, in this case, has to combine the 2 equations as shown in the third equation. So this is what we call simply the hydrological cycle in a simple concept. Details for modeling, we'll look at different variants of these equations. You can come across different literature. If I will share some of the reference books that I indicated in the announcement regarding the materials for reference. Yeah, I have electronic version, but it's not really legal. So I'll share with the coordinator to share with you. And please use only for yourself. Yeah, use only for yourself. It's not legal. In principle, the university should buy for you one. But I think because of resources are limited, and also your focus area is more of a diverse focus areas, and your interest in the books that I sent is not going to be uniform. So the best way is for you to get this material, but keep it to yourself, not sharing publicly on social media, wherever, because you'll be banished for that one. Now, looking at this water balance or hydrological cycle, you can see that runoff constitutes about 38%. And then we have evapotranspiration, which consists for around 24%, and then canopy interception about 90%, and then we have soil evaporation from bare soil. You can see it is around 21% and so on. So can you see all the figures here? Can anyone respond? You see clearly the labels? At the end of the lecture, I'm going to share all the presentation with all of you. So you don't have to be worried. You have a close inspection of the PowerPoints afterwards. But just to follow what I'm discussing, I want to know if you can see clearly the different figures and levels. Can anyone respond?
Yes.
You can. All right.
Yes.
All right. Thank you. Any question up to this point? This part is part of the hydrological cycle, and I said water vapor. Water is a very important component of all the greenhouse gases. We know this Clausius-Clapeyron equation is the main governing equation that detects climate change. From this equation, we can see that wet get wetter, dry get drier. Basically, the water holding capacity of the atmosphere depends on temperature. Depends on temperature. If the temperature is warm, the atmosphere has more capacity to hold water. If the temperature is low, the atmosphere can easily get saturated and cannot hold water. So this is what it means. Water vapor has a very important role compared to other greenhouse gases. Basically, it's central to energy flows within the climate system by basically controlling transmission of radiative energy between surface, atmosphere, and the space. Also through transfer of latent heat from the surface through evaporation to the atmosphere through precipitation. As I said earlier, all this phase change in water from liquid to gas, from gas back to liquid, and from liquid to solid involves latent heat release or uptake, and this is an additional energy that drives the climate system. So basically, I already said about the role of water vapor. For instance, amount of water held by atmosphere, as I said, is controlled by water vapor pressure. And as you can see, an increase of 1 degree centigrade at less than 20 degrees centigrade increase the water holding capacity of the dry air by 6%. Similarly, at 0 degree and 80 degrees, the water holding capacity increased by 80 and 20%, respectively. You can see dramatic change in the water holding capacity of the atmosphere. And I think Professor Andreas Fink, he told me he's going to focus on this one. He must have given you a lot of examples where the CC equation has very important role to play in terms of atmospheric processes and energy balance within the atmosphere. I just want to show this schematic. Perhaps you have come across this in the past, but I'm not sure because of your background, whether your background or your exposure in the past has allowed to have something like this. This is a schematic where you see the different components of the water cycle. The precipitation, the clouds you see somewhere at the top, and then you see on the land surface we have different layer, zone of aeration, the top layer, and then of water table fluctuation, the middle one, and then we have zone of saturation, the bottom one, and of course the surface runoff and the permanent stream flow as a simple sketch to give you how different components of the hydrological cycle interact with each other. So, in fact, in this case, you can clearly see that groundwater is a critical resource, particularly in this region. The particular resource of fresh water, and it estimates that we have around 4.2 million kilometer cube of groundwater within the first 2.5 kilometers of the surface. And if you have a borehole somewhere very shallow, covering only up to the zone of water table, a little close to the top of the water table, these kind of boreholes are seasonal because there is a fluctuation in the water table depending on whether you are in a dry season or a wet season. And then if you have a borehole which is deep enough to reach the zone of saturation, the source of the water you get from this borehole is not seasonal dependent, because here you have water throughout, regardless of the input from precipitation and so on. So to see some of the highlight concepts regarding with the water balance or hydrological cycle, I would like to give you some figures. For instance, we can look at the different reservoir. The whole of the Earth's water estimated to be somewhere between, you can see this is terrace to 9, 1.3 terrace to 9, between 1.3 to 1.4 terrace to 9 kilometer cube. Ocean accounts almost for 97% of this water. All total water is in the ocean. Freshwater is around 35 million kilometer cubic, which is accounts for 2.5 to 3% of the total water. You can see the fraction of reservoir in percent in the third column. And ice and the snow, they are also part of freshwater, very small. Well, it's of course, as a result of global warming, maybe this will be additional resource of fresh water. But as you know, it's not recommended. When you get fresh water by melting ice in the polar region, what's going to happen is you are going to substantially change the albedo of the Earth's surface, and that will increase the solar energy input. You know, what I mean by albedo is the incoming solar radiation from the sun. Only 70% is absorbed, 30% is reflected back because of the nature of the Earth's surface, which consists of ice and snow, consists of bare lands, buildings, vegetation, and so on. So if you change this composition, you are going to alter, you are going to change the amount of energy that is reflected back to space. If you absorb more than the 70% that we are currently absorbing, now that is going to create additional global warming. So even even if you stop, let's say, emitting all greenhouse right away, global warming will continue because there are still greenhouse gas in the atmosphere that will increase the temperature. As a result of increasing the temperature, the ice and snow will begin to melt. And when they melt, and then there will be a reduction in the albedo. That means you are going to absorb more than 70%. Could be 73, 74. It depends on the severity of melting. Yeah. So it's a very complex system that you touch somewhere and you cannot switch off the effect by doing the same process, because global warming or climate change is affecting so many things. Albedo of the Earth's surface is critical in climate change. That's why deforestation, even afforestation, beyond what's necessary, is not recommended, because you are going to disturb this balance. You are going to affect the 30% albedo of the edges. If you change that by any means, you are going to affect the energy input to the edge. And if you affect the energy input to the edge, you are going to change the temperature. So these are important components. Ice caps, glacier, and permanent snow, they account for about 60.87% of the fresh water. Fresh water is only about 3% of the total water of the whole Earth's water. And Antarctic ice, snow, Greenland, these are small areas, but they have substantial water within them because of the ice. Surface water, fresh water, is only about 0.3%, very small. In the lakes, we have about 87% of surface fresh water. In swamps, it's around 11% of surface fresh water. When I say surface fresh water, it's only 0.3. Yeah, it's not big in terms of percentage. It looks big, but it's 87%. 87% of 0.3% of fresh water. So rivers, about 2%. Atmosphere, you can see the estimate is varied from 12,000 to 50,000 cubic meter of water in the form of water vapor, cloud, and so on. This water will be moving between different components of the Earth's atmosphere system. Precipitation, for instance, you get precipitation from atmosphere to the ocean or land, and the flow rate, as you can see on your right side, is 505 cubic kilometer per year. From atmosphere to the ocean, we get around 398. From land precipitation, atmosphere to land surface, evapotranspiration, ocean, land surface. You can see different components. So basically, the flow rates, the exchange, the interaction between different components of the climate system is governed by these flow rates when you look at hydrological cycle or water balance in general. It's also important to look at not only the transfer of water between different components, between different reservoirs, but also it's important to know the time they spend in a given reservoir before the water stays is converted to some form and moved to the other reservoir. For instance, ocean, the resident time water is between 3,000 to 3,230 years, very long. Glaciers, we are basically referring to higher mountains and in the polar region. So the water there in the form of mostly ice can reside in the same place for from 20 years up to 100 years. Seasonal snow cover. Seasonal is snow can increase, decrease. For instance, snow can increase in winter. The snow extent could move further to cover, let's say, Europeans, American, mid-latitude areas during winter, but this snow will retreat or disappear during summer period. So this seasonal snow will last only from 2 to 6 months. Soil moisture has a very short residence time. It's 1 to 2 months. And groundwater, when you talk of groundwater, you can look at shallow and deep one. The shallow one has a residence time, lifetime of 100 to 200 years. Deep ones up to 10,000 years. Water in the lake can stay there anywhere between 50 to 100 years. Rivers 2 to 6 months because it's just like soil moisture. It's mainly seasonal. Atmosphere has the highest short lifetimes in the atmosphere. As I said, all process of phase transition is going on from liquid to gas, from gas to solid. Yeah, you can go that route as well. And this phase transition allows also because of high movement. The atmospheric circulation is very strong. Transport is taking place, and let's say air from the tropics is moved upward and also moved to the polar region and come back to us close to the surface. So there is this atmospheric circulation. I don't know whether you have some knowledge in that direction. The atmospheric circulation will allow to move water from place to place, and the radiant time of water vapor, or water in general, not water vapor, water in the form of vapor and ice and water, liquid water, has only a lifetime of 9 days. So there is high variability. This is very high variability in terms of water amount because of this short lifetime. Now, that is all about the water balance. Because I hope you have this exposure from different courses, because some of the courses I have seen will not deal with what they're supposed to teach without touching this aspect of the water balance. So this is just a kind of refresher, I believe. And now we look at impact of climate change on different component of the climate system. This is mainly taken from IPCC report, the latest one, 2022. And you can see here the different colors shows confidence in the findings. High or very high is shown in blue. And then this kind of purple color is medium confidence. And then if you see a shade is low confidence. If you see a white circle, there's no enough evidence to make the conclusion. So here, the effect is also categorized into global, African, Asian, Australian, and so on, desert, and so on. Sorry. So here, basically, change in ecosystem structure, terrestrial freshwater. For instance, globally, you can see a strong confidence. There is an impact here of climate change. On the ocean also, this is a strong change in the ecosystem. In Africa also, there is a strong evidence that links climate change to ecosystem change. And on species range shift, change in the species range, on the terrestrial global level, you can see it's all blue. It's all blue in the middle row. And then if you see Africa, terrestrial range shift, land surface range shift, on the land surface, there is strong confidence, range shift in the freshwater and the lakes. Basically, there's not enough information. There is no information. And change in timing of growth phenology, for instance, of plants on terrestrial, on the land, and in the freshwater, in the ocean. You can see strong confidence. But when it comes to Africa, again, because of limited data, the impact of climate on change in timing of ecosystem change or vegetation growth is either low or no data. So that is what the IPCC found out. And another area where we can look at the impact of climate change from IPCC finding. IPCC, of course, compiled findings of different researchers. It's not its own research. They just have to put different findings from different groups together. So this is a very complex, diverse research areas. They looked at human system, for instance, water scarcity, crop production, animal and livestock health and productivity. They looked at fisheries yields and aquaculture production, how they are affected globally, as long as current science is concerned. They looked at global Africa again in terms of even by sea and so on. And again, the color represents strong blue is high confidence, and then the purple color is medium, and the shadow shade is low confidence, and white circle is limited data, no evidence, no sufficient evidence. Yeah? And we have also plus and minus. Minus is for increasing adverse effects. Plus is for increasing adverse and positive effects. Yeah? For positive effects, sorry. If you see plus, minus, then the signal is combined. So looking at Africa, water scarcity, yeah, there is water scarcity, and this is confirmed, but the confidence in the observation so far from compiled literature is at the level of medium confidence. And impact on agriculture crop production is very strong, and it's a negative one. And animal and livestock health and the productivity, then yeah, it's a negative effect, but the confidence in this studies is rather low. Impact on fishery yields and aquaculture is also strong on Africa. Just focus on Africa, and you see that the confidence is still medium. It's still a lot of work to be done to come to concrete conclusion as far as climate change on human system is concerned. The other humans is related with health and well-being, infectious diseases, impact of climate on infectious diseases, heat and malnutrition, mental health. Climate will affect all this. Displacement due to climate change. Evidence at the global level is very strong, mostly negative, particularly on heat, mental health, displacement. The evidence is very strong. But when it comes to infectious diseases, the confidence in the understanding is medium. For Africa, there is strong evidence except for the mental health. Here, you know, because of the economy, not much data is archived. You know, mental health data should be obtained from hospital, clinic, and so on. But in Africa, because of scarcity of health services and the way we manage data, we don't have much information. So the confidence in terms of mental health is rather low. Actually, the evidence is not there because of scattered data. So that is the impact of climate change on different systems, as you can see. Impacts, I think this will be the last in relation to impact of observed impact of climate change. Impact on cities, settlement, and infrastructure. These are human systems. Inland flooding and associated damage in the city due to climate change. Flood stream, and this damage is coastal areas and infrastructure. Damage to infrastructure. Damage to key economic sector as a result of climate change. At the global level, the evidence is very strong and negative. And when it comes to key damage to key economic sectors, yeah, the data is not that robust. So it's, of course, it's a negative and a medium one. For Africa, again, it's all related. It doesn't mean that we don't have the impact, but the way we collect data is not sufficient enough. So the IPCC were not able to convincingly conclude that climate change has impact on cities in terms of inland damage, yeah, and so they put it as medium confidence of impact of climate change on cities, settlement, and infrastructure. Key economic sector, of course, there we have a lot of data, because of the fact that you know, our adaptation and we are very much vulnerable to climate change. A lot of the economic sector are very much vulnerable. So you can see a lot of data is gathered in this section, and climate change is affecting Africa so much in this direction. In conclusion, when you look at observed climate change as summarized by IPCC, IPCC stands for Intergovernmental Panel on Climate Change. It's a United Nations body which coordinates actually research related to climate change. They don't do research on them by themselves, but they really coordinate researches from global research centers. Because we know that climate change is causing a lot of damage to different aspects of the climate system and our livelihood, the IPCC also went to see what's going to be, what kind of damage we expect, let's say, if you continue emitting greenhouse gases as it is now. If you really make some intervention through technological development or adopt new technology to mitigate the impact of climate change and so on. They have different scenarios that lead to different level of global warming. 1.9 watt per meter squared warming, 2.6 watts, 4.5, 7.0, 8.5. So this is the, if you follow this socioeconomic pathways, we expect by the end of the century, we expect 1.9 watts per meter squared increase in energy surplus. And if you follow this social economic pathway, we follow 2.6, and the other one is SCP2, then that will lead to 4.5 excess energy by the end of the century. If you look at SSP3, it's going to be 7 watt per meter squared increase in surplus energy. That's that surplus energy, basically, you can translate also to temperature, because there is no direct translation, but as long as you have excess energy, that will increase the temperature. And as you can see, an increase in this number here means the temperature, corresponding temperature, is going to increase as well. They did different analysis. You can see that they extend up to 2100 end of the century. And if you follow these lines, for instance, SSP3 7.0, this is the likely path in terms of temperature change. You can see by the end of the century, the temperature is going to be around 4 degrees centigrade. But it's likely the range could be anywhere from 3 to 5. The shaded area shows you the possible range, because we are not certain the effect, because there is no direct translation of excess energy to temperature. It depends on so many factors. And when you consider all these factors, it can go anywhere between 3 to 5 degrees centigrade increase in temperature by the end of the century. What is the implication of this temperature change on different aspects of the social economy? We'll see. So you can see that this change could lead to different things. You can see different sectors, the human sphere, and then you have this the wild ecosystem. You can see the domestic animal and the human ecosystem, and there is an interaction between all this, and this is likely going to increase disease transmission from different spheres into the other sphere. As you can see, an overlap between all these 3 spheres. And I'll share with you the PowerPoint. I'm not going to read all of them. You can see different components, and these are all the summaries of IPCC. And I hope you have got we can easily download. This is a free document. It's very big, maybe not that attractive to read everything, but when I share you this PowerPoint, you may follow, you may use this as a guiding document to look at the different section of the IPCC report. So impact of climate change on the hydrological cycle. To understand the impact of climate change on the water balance, we need to first look at the watershed. First, we look at the type of watershed. Watershed basically categorized in terms of size. Based on size, you can have this different category from micro to large watershed. You can have watershed in terms of area, macro. This is just when I say size, it's basically about the flow. Here it's about the area here, and then based on shape, different water shapes, square shape, triangular shape. I think these are you can find this from literature. These are just type of watershed, and watershed has functions, 2 major functions. One is hydrological function, and then there's an ecological function. The hydrological function is basically collection of water and also storage of water, discharge of water. So watershed has these 3 laws in terms of hydrology. And when you look at collection of water, you can see collection of water from adjacent watershed, from rainfall, from snowmelts. That's how it gains watershed gain water. Storage of various amount of water with different duration. Discharge of water as a runoff. It will discharge as a runoff. So this is the function of watershed. Ecological function, basically, you can broadly look at 2 aspects. Provides pathway for various chemical reaction, useful for maintaining the ecological balance as a system, okay? And provides and converts space for flora and fauna. So these are the 2 ecological functions of a watershed. So once we know this, then we can talk about impact of climate change on the hydrological cycle. Watershed is vulnerable to climate change, and we have a positive factors, vulnerability factors, and then we have also a negative ones. The positive ones are on the right side of the screen, I guess, from your side, and the negative one, such as area of forest cover, impervious area, average watershed slope and so on are on the left side from my side. These are the negative ones. And basically, what you see in the boxes, the different rectangular boxes, is the impact of these factors, what the rainfall factor has, evapotranspiration as one of the factors, positive factor, area of depression, runoff. So you can see in the box the different roles of these factors. And for the negative ones also, again, you see the role of different factors in the boxes. To understand the impact of climate change on the watershed or on the hydrology, people have defined vulnerability indexes. I think Marilla on Thursday is going to talk in details, maybe specifically going to what this means in all these cases. So I'm not going to really discuss in detail apart from mentioning. So we have different variety of indexes available in the literature: water availability index, index of water scarcity, vulnerability of water systems, environmental sustainability index, water poverty index, social water stress index, stress indicators, and so on. And on this side also, you have different indexes, and clearly the reference for anyone who want to specifically look at these indexes. You can find the original literature from this publication by these authors. So now I want to show you the impact of climate change on the biodiversity loss for different scenarios. If the global temperature increases by 1.5 degrees centigrade, by 2 degrees centigrade, by 3 degrees centigrade, and by 4 degrees centigrade, what will be the change in the loss of terrestrial and freshwater biodiversity? So clearly, you can see in the color bar down at the bottom, you have yellow, and then the extreme ones are red. Yeah. So as the temperature increases, we are moving from yellow color everywhere globally. Literally, there is a difference between different parts of the continent, but you can see clearly from 1.5 degrees centigrade temperature change. If you go to 4 degrees centigrade, you reach percentage of biodiversity loss is going to be beyond, let's say, 70%. You can see the Southern Africa region, which you are interested. Look at the top figure here, 4 degrees centigrade. It's almost all the SADC region except the coastal areas is more than 70% biodiversity loss, freshwater biodiversity loss. So climate change has a really high impact on loss of terrestrial and freshwater biodiversity. We can also look at the number of months per year with severe water scarcity as a result of climate change. These are basically observed. Number of months in which water scarcity more than 100%. 12 months is all throughout the year, which is dark here, dark brown color, and then you have kind of close to yellow color here, 0. So looking at Africa, that's where we are interested, where we belong. The only area with almost zero water scarcity, there is no scarcity throughout the year, is the areas, areas which is covering DRC and Tanzania. These regions are the Congo Basin, where Congo Basin is located. You can see there is no water scarcity here. But we look at the southern, almost the whole south, I wouldn't say the whole SADC, but the majority of SADC areas, again, there is water scarcity throughout the year, as you can see, close to 12 months, except the coastal area of Mozambique and part of South Africa. And the Sahel is the same. The Sahel is the same, but the equatorial Africa, which is around this area, is around close to 5 months. Basically, the winter months are the one where you have water scarcity. So climate change is impacting all these cases. Yeah, there are also climatic and non-climatic impacts. As you can see here, water quality and safety can be impacted. If you look at the figures, water availability down at the bottom, and then accessibility to water services, and then water management. All these combined will give you aggregated global water security index. Yeah, less secure is brown color, and more secure is like green color. With that understanding, if you look at Africa, most of Africa is somewhere between yellow and brown, as you can see, and the Southern Africa part is somewhere toward the secure area, which is not green, but somewhere here. This is partly because of the groundwater. So if you look at the whole system, the whole flux in natural and human system, you can have this schematic how climate affects different components. You can see groundwater recharge here, groundwater withdrawal because of different human activities, energy production from water, irrigation from groundwater. These are all accounting for very small amount of water use. River discharge, groundwater discharge to ocean, for instance. This is amount of energy. And then water sanitation, hygiene will also take up. Industrial water withdrawal is also less than 1%, as you can see here. Municipal water withdrawal is also very low. Yeah. Green water use for agricultural purpose, land evaporation, land precipitation. So these are the whole component: ocean to land water vapor transport. So this shows the whole water cycle that includes the human component. As I said, climate has almost 6 components: atmosphere, the hydrosphere, the biosphere, the lithosphere, and the cryosphere, the ice, and then we have the anthroposphere, the human component. So these all components are interacting in this picture, affecting the water cycle. So irrigation is another area where the hydrological cycle is impacted because we use irrigation for agricultural purposes to feed the increasing number of population that will alter, obviously, even the precipitation, because you are taking water from the hydrological cycle, from the groundwater, for instance, but you can increase also local precipitation, because as a result of irrigation, you are going to have crops, and crops will lead to evapotranspiration. That evapotranspiration basically will be converted to Precipitation is a process because there will be vertical ascent of the water vapor, cloud formation. There are different processes as a result of enough moisture and sufficient dynamics. So areas where you have widespread irrigation system, it's likely that you are going to increase local precipitation as a result of release of water to the climate system. You can also alter, precipitation from evaporation of water from irrigated land will not be also staying in the same place. It can be transported, it can be advected by wind to other places, such as monsoon system. Yeah? So this will affect actually the timing onset of rainy season, for instance. Yes? Did I hear? Are you halfway? Or do you have a question? All right. So climate is not the only factor that impacts this hydrological cycle or a water balance, but also, as I said, irrigation, because irrigation itself is a mechanism of water abstraction, so it affects the water balance. But as a result of irrigation, you have more water vapor into the atmosphere, which will lead to cloud formation and more rain in the same area as a result of the irrigation process. And it can also remotely affect other places because the moisture released due to irrigation can be transported by wind to other places and change the regular monsoon system, for instance, in terms of timing of onset of rainfall during monsoon, for instance, the Asian sector or over in the West African sector. Land cover change also affects evaporation and precipitation. It also affects interception of precipitation by vegetation canopies, infiltration, and runoff. So I'll show you later on how this works specifically for the region itself. Apart from the fact that by changing the land cover, you are going to change the albedo, which will affect the incoming solar radiation. And change in the incoming solar radiation means change in the climate itself. So it's a kind of positive feedback with each other. No? First, land use change leads to change in the land cover, and that will lead to further enhancement of climate change. So hydrological cycle will be affected as a result of land cover, and I have actually a research work that I'll show you later on. Urbanization is another non-climatic factors that will affect. Again, this is in terms of changing the albedo, in terms of the way water circulated between different components is affected as a result of surface change. Surface permeability is going to be affected by urbanization. An increase in fast runoff and flooding as a result of urbanization is very common. Local rainfall can be reduced as a result of decrease in moisture, return to the atmosphere within the urban environment. So there are many other factors that affect the hydrological cycle apart from the climate itself. I went to look at, I think, let me stop here for a break of 10 minutes. We'll meet at, now it is 27 past 10. So we'll meet at 37 past 10. Those of you who don't want to go and they want to engage with me, I'm still around, we can talk. Thank you.
Thank you so much, Prof. Colleagues, 10-minute break, we reconvene.
Colleagues, can you start?
Hello, Prof. We had agreed 10:37 and online, I just want to check.
Yeah.
Yeah, we have our online participants. I'll suggest we continue because we are 10:37 we start.
Yeah, you're right. Thank you so much. So earlier I stopped talking about the different non-climatic contribution of contribution towards the impact on hydrological cycle. Now I want to show you the general global distribution of the different components of the water balance, precipitation, panel A, evapotranspiration, runoff, as you can see, discharge, and groundwater recharge, and then soil wetness. This shows a global distribution in terms of precipitation in millimeter per year. I think those of you who knows the who are familiar with climate, I think precipitation is more obvious. From Africa, the wettest part is the Congo Basin, as you can see in this color. The color bar ranges from 0 to 5,000 millimeter per year. And the Sahel is completely dry. And also in the Kalahari here, along the Namibia coasts and part of South Africa coast, you can see similar things, very dry. But the rest is around 500 to 600 millimeter per year in terms of precipitation. Evapotranspiration is comparable in the Southern Africa region. In some cases, actually more than the precipitation. This is typically a characteristics of arid and semi-arid region. And then runoff is also very limited when it comes to Southern Africa region, Congo region. The rainfall and runoff goes together. Wherever we have high rain, you have a lot of runoff, as you can see in panel C. Discharge here is in D from river discharge, basically. Again, big rivers are in the Congo areas and also along Ethiopian mountains, the Nile River here. So you can see a lot of discharge from this region in the Lake Victoria area, in the Kenya, and so on, around the Rift Valley. But when it comes to Southern Africa, yeah, it's very, very limited, very limited. Ground recharge is also limited, in fact, even if it's a major source of water, fresh water in the region, it's very limited according to these studies. Soil wetness for the Southern Africa region, soil is also dry. As you can see, most of, particularly the western half of the SADC region is basically dry soil as compared to the eastern side of the SADC region, as you can see in this map. Now we can also look at the trend. That was just a climatology. What we have seen here in the previous slides is the mean climatology, mean long-term annual precipitation, annual evapotranspiration, runoff, river discharge, and groundwater recharge, and soil wetness. But this mean condition, annual mean condition, is not constant, changes from season to season, even under normal circumstances. But on top of that, we have also climate change that will alter these flows or all component of the hydrological cycle. And what you see here is long-term trend in millimeter per day over a 50-year period, for October, September, mean runoff, what is you see here. And then in the lower panel down here, it's a long-term trend for annual precipitation. So the long-term change for annual precipitation at the bottom, as you can see, is the red ones are where you have decrease in precipitation. The whole Africa, most of Africans are undergoing decrease in temperature, at least when you look at the historical precipitation. The future projection has a mixed signal. We didn't talk much about that because the projections are basically scenarios, and scenarios are not what's going to happen. It's just a possible pathways of development. So we may follow what is proposed. We may not follow, depending. The actual circumstance may greatly depart from the proposed scenario. So you cannot clearly say that this is going to happen. But if these conditions follow this line, we are going to expect this kind of change. So it's a scenario. It's a kind of if this happens, then this is going to happen. But what we see here is just the actual. And the good thing about the SADC region, particularly the area where you have deficit in most component of the water cycle, we see that there is a small increase, at least small increase, about basically 0 up to 0.15 millimeter per day over a 50-year period. We are going to get very small change in precipitation. It's of course substantial because this is a change over a 50-year period. So if we are getting 400 millimeter today, then according to these studies, after 15 years, you'll be getting something around 402 millimeter. A small change, but it's not. But it's a positive one. And of course, even in the increase in the precipitation, depends. You could get a lot of precipitation change, but if this change in precipitation comes in the form of extreme event, we are going to talk about it, it's going to be as damaging as deficit in rainfall, because to lead to high runoff, flooding, and damage of ecosystem. Also contaminate the available fresh water. So there are so many factors that can be cited not to favor a high amount of increase in precipitation. So if you get really a seasonal rainfall, well distributed over the let's say the rainy months, that is what we say, it's a very good change. So the change, if the change is in the extreme, either in the extreme high or extreme low, it's not going to be very good. So again, for the surface runoff, it's going to decrease. It's going to decrease. That basically shows that this increase in precipitation is coming mainly from extreme precipitation that takes place maybe once in 10 years, not much. So that is why you don't see any change also in the runoff. There are other studies that looks at land precipitation, and discharge from the continental river. Clearly, you can see that there is a very clear assertion. The solid line is basically the discharge, and the dashed line is the land precipitation taken from GPCC. This is a global data set you can access. Maybe I'll give you the link to this data, or one of my colleagues on Thursday or on Friday, they will give you this data also. So you can see clearly the association between river discharge and rainfall is clearly positively associated. And the discharge, continental discharge, is linked with rainfall. And rainfall, we know, is also linked with INSO. INSO is a very important phenomena globally, particularly for Africa. We have two phases of INSO, a warm phase and cold phase of INSO. The warm phase of INSO is not really has a negative impact in terms of precipitation over Africa, but not uniform everywhere. But generally, the warm phase is El Nino, and the cold phase is La Nina. Yeah, La Nina. So El Nino, during El Nino, we get drought almost everywhere in Africa. During the same period, you get excess rainfall in the other part of the globe. So the warm phase is not good for Africa in general. And of course, that you can look at the text. The text will talk about the different section of this graph, and I'm not going to talk about it in detail. I'm mainly focusing on the general picture of what you see on these slides. So trend in annual precipitation, again from IPCC, you can see for every degree increase in temperature, what is the impact on precipitation, on annual precipitation trend in terms of percentage, yeah, in terms of percentage. Clearly, the green ones are where you have a positive change, increase in precipitation. The brown ones, brown colors here, going from 0 to minus 50% is a decrease in precipitation. So Africa is generally experiencing decrease in precipitation. Level of the familiarity in terms of annual precipitation change. There is a different class here, from dry to wet, unknown wet, unusual wet, and familiar. Over the globe. Unfamiliar is events, wet or extreme dry events that happens at least one in every 6 years, and unusual ones are events that happens, a dry event or warm event that happens once in every 50 years, and unknown is basically something that we have never heard of in the last 1,000 years. So that's the kind of, because this is just for basic understanding, looking at the different kind of extreme precipitation, extreme dryness, extreme wet condition that is happening due to climate change. So if you're looking at this picture, you see the white ones. When you see white shade on the map, it's basically there's nothing of extreme wet or dry conditions. So the precipitation in these white areas are normal. But if you see color toward this brown color, or if you see something toward this green or blue color, then the blue represents extremely wet conditions. So Africa has very few places, isolated places, where you get extreme wet conditions. When it comes to the SADC region, along the coastal region, both on the east and west side, you will have unfamiliar dry condition, which happens at least once in every 6 years. So that's how we can understand climate change. There are different ways of describing impact of climate change on the water cycle. This is one way. Basically, what you see is a frequency before climate change, or a kind of return period. If an event happens once in 1,000 years, it's very rare event, as unknown. If it happens once in 50 years, it's unusual. If it happens once in every 6 years, it's unfamiliar. And what we are experiencing in the region, in Africa in general, is covers all these spots actually. For instance, I'll talk later on or tomorrow about drought of 2015-16, which was very severe and has high impact in the region. So we are experiencing the whole spectrum of extreme event when it comes to precipitation, also when it comes to temperature as well. Usually in the Southern Africa region, when you talk about precipitation or rainfall, the best season to talk about precipitation is the summer season, which is December, January, February. Of course, the rain in Botswana, as I know, which is the same for Namibia, goes all the way from October to March, April period. It's an extended season, but the peak season usually can be considered as December, January, February period. So what you see on the top panel here is change in precipitation for every degree increase in global temperature. It's in percentage, and you can clearly see that the annual is quite different from the previous one. Is annual because it includes the whole months from January to December. Because the Southern Africa region is mostly dry, except December, January, February, the picture is not very clear. But if you focus on the wet season itself, which is a critical part actually, the rest are already dried. We don't care whether they are dry or not that much, except for temperature. So you can see that there is something blue in the central part of SADC region, and then we have a gray color over the eastern part during this season. So this is a wearing actually. In terms of percentage, this goes all the way between -20 dry condition to positive 20% dry condition. When you look at the seasonal rainfall, which is the main rainy season for Southern Africa. Actually, just for contrast, if you look at Europe here is the region which benefits the most from climate change. They will get rainfall if that is considered as a positive. Yeah, it depends, of course, how the rain comes to the surface. If it comes in the form of heavy extreme rainfall, that is even dangerous. But if it comes over distributed well in time and comes at a regular interval, that could be is a positive thing for this region as compared to what we are experiencing in the South Africa region. Other parameters that can be used to describe precipitation is obviously precipitation, maximum precipitation that we get in one day. This is Rx one day. You can see when you talk about climate extreme, that refers to temperatures, that refers to rainfall, that refers to combined rainfall and temperature. We call it compounded event. Is described through this index. We call them indexes, climate extreme indexes, Rx one day. You see Rx one day, Rx 5 day, Rx 10 day, and so on. So these are indexes that describe extreme condition related to precipitation here at the bottom on the left side of your screen. And here again, the trend is that the maximum one day precipitation is increasing. So the maximum one day precipitation, that means change in precipitation is mostly focused in the extreme part of the rainfall distribution, not at the middle, not at the bottom. So that increase is not something that is that we want to have because it has high impact in terms of flooding and damaging resources. So the Southern Africa region clearly shown here by green, particularly the eastern part of South-Sadic region. Other parameters that we can use at the top, it is for June, July, August. Anyways, this is this winter for the Southern Africa. That's why we see white color here. So you don't see any signal. So we are, as far as Southern Africa region is concerned, June, July, August is winter, dry season, and nothing to talk about. But the rest of Africa clearly has some change in this pertain because this area, particularly around Equator and north of Equator, will get a lot of rainfall during June, July, August. And what you see here also is a negative picture in terms of impact of climate on precipitation. So there is generally a decrease. It's not uniform, as you can see. There are places where we have increase in precipitation. There are places where you have decrease in precipitation. So within the same region, there is a mixed signal. And this mixed signal is coming because of difference in topography, different in proximity to water bodies and so on. So there are different local climates that responds to climate change in a different way. That's why you see mixed signal when it comes to rainfall during June, July, August over equatorial and northern Africa region. Another parameter at the bottom you see here at the bottom is CDD. CDD stands for continuous dry days. Continuous dry days. So this is also a parameter that commonly used in climate to describe impact of climate on the water balance or the hydrological cycle. So this is a trend per 10 years. And clearly you see that the continuous dry days here, I'm focusing mainly on the South Africa. Look at the Southern Africa part, the SADC region, is shown in brown color. So there is an increase in continuous dry days. Unfortunately, this is happening over part of SADC region, which is normally receiving a lot of rainfall. When you look at the Kalahari, the desert region on the western side, is shown by green color here. Green color is basically decrease in the number of continuous dry days. So that means the area which used to be dry is getting some rainfall. So the dryness, the dry days are interrupted. It's not continuously dry. You get some sporadic rainfall that interrupts the dry sequence of days. So this is not what we want. No, if we hope, if you want to wish that we get something from climate change, you'd have expected more rain on dry areas, yeah, and the same amount of rain in wetter areas. But the situation, as far as this study shows, which covers the period from 1950 to 2018, which is around 38 years, up to around 88 years actually, 50 years from there, 68 years, is showing that the situation in the SADC region is very severe in terms of dry conditions. Soil moisture is another factor that one can see. Soil moisture studies are, there are measurements taken about soil moisture at national meteorological services, but the stations that are monitoring soil moistures are not many. They are limited to very few stations. So definitely they don't give you this kind of global picture. Therefore, some of the data that is used here is satellite based. Satellite can estimate, cannot make exact measurement, can estimate the amount of soil moisture over a given area. So here, surface soil moisture change in percent is shown. Greener means basically an increase in soil moisture. Brownish color means a decrease in soil moisture. Again, if you focus on our region, the situation here is towards a negative decrease in soil moisture is happening due to climate change, at least as far as the last from the period 1978 to 2008 is concerned. Now, that was just the existing situation from observation, in-situ observation, gauge observation, and remote sensing observation from satellite, because we have many satellites since the 1960s, and some of those are able to provide some of the information that we just discussed. Now we can look at the change in this condition in the future. Actually, this is a study done in under the coordination of IPCC, Intergovernmental Panel on Climate Change, CMIP5. This is the previous report. We have now the sixth report, which is a recent one. The difference is, there is some difference here and there, but generally the outcomes from these studies are comparable. So on the top panel, panel A, B, C, and D, you see precipitation change from under scenario RCP 4.5, and then soil moisture change for the period 1790 minus. You can see this is we are subtracting the future change, the future soil moisture from the historical soil moisture, which is represent 1970 to 99. Yeah. So you use the base period. We call this the historical data period, which is used as a reference, is the base period. Usually, when you calculate these changes, you use something around 20 to 30 years. 30 years is standard. So 30 years base period shows that there is a change under this scenario. So for precipitation, what you see here is a decrease, again, very consistent with what we have seen also in the observation. But the rest of Africa, particularly north of the SADC region, Eastern Africa, Equatorial Africa, most part of the Sahel, sub-Saharan regions, becoming wet, relatively wet, relatively wet. This is a percentage change anyway, compared to the historical period. Soil moisture, definitely when you get most rainfall, you should expect also a positive change here. If it's a positive one, if it's a negative, obviously a negative. So these are consistent with each other. Soil moisture is also decreasing as a result of decrease in precipitation in 2070 and 1990 as compared to the base period. Evaporation change is also, there's a decrease in evaporation. There's no water what's going to evaporate definitely. The only thing you expect is transpiration from vegetation. The seasonal vegetation may not be there. The long-lived vegetations are the one only providing some of the water in the form of transpiration. Total runoff, also consistent with what you see about moisture. So these are all related, and the models are producing very consistent picture of what is going to happen if you follow this trajectory, if you follow these pathways of economic development, which leads to different emission levels of greenhouse gases. So RCP 4.5 is basically under this scenario. It's a modest one. There's going to be an increase in surplus input of energy of about 4.5 watt per meter squared by the end of the century. And this is translated to change in precipitation, change in soil moisture, change in evaporation, change in surface runoff, as well as change in temperature. We have seen the temperature change in the previous slides. I think the following slides are more or less, we'll be back into these topics later on. It is about historical risk of different climate events, extreme events, mainly hydrological events such as flood, and also the projection. So I think Mariela is going to talk about this in detail, but I'll give you what has been summarized by IPCC. So if you look at the color bar, the flood water depths, low is white color, and blue is very high, greater than 10 meters flood water depths, flood water depths. So if you can see the flood water hazard here, and historical on the left and projected on the right. So clearly, if you focus on Africa, the whole of Africa is moving from high 5 to 10 meter flood water depths to somewhere around more than 10 meter flood water depths. But for the Southern Africa region, only the coastal, the eastern part of SADC region is affected. The other part is very, very low in terms of flood water hazard. This is flood vulnerability, basically level of protection against flood water. For the historical period, for the projected period, you can see, because I think Mariela is going to give you also the definition how hazard, vulnerability, exposure, all these combined together are related with risk. She's going to talk in detail because I'm not going to touch in detail, but I'll give you pre-hand information on what is expected globally and in our region. So vulnerability is, for instance, if you are not able to protect yourself, So here, what you see is most of African countries are highly vulnerable to flood water, very high. You can see greater than 5, the yellow, strong yellow color at the other extreme. And then the rest of Europe, you can see this is mainly economical. There is economical factor here. Europe, America, they are not really, they are in the high range, not in the very high extreme in terms of vulnerability. For projection, focusing on Africa, nothing is going to change. We'll be still vulnerable to flood water because there's no much expectation in the coming 15 years in terms of infrastructure that protect us against flood water. Drought is another extreme. Here you can see a map, current global drought risk average for period from 901 to 2010, yeah, and then the first 4 panels on the left, and the next 6 panels on the right are projection. Yeah, this side is projection on your right, and the 4 big ones are for the current situation. Drought hazard A, drought vulnerability B. Here you can see drought exposure, and then drought risk. So these 3 combined will give you the risk. So if you are highly vulnerable, if you have high exposure, and there is hazard there, the product of all these 3 will give you drought risk. So clearly, looking at drought hazard, yeah, there are a lot of drought compared to flood. Drought is going to affect the region very much, as you can see in this color here. The blue part is very high drought hazard, and then if you see white color, very low hazard, it's a hazard index, and then you have a vulnerability index here, which runs from anywhere 0 to 1, and here again, white shows vulnerability is rare. 1 means with this color here, very high. So again, Africa is very much vulnerable to drought, as you can see. And then exposure, in terms of exposure, again, the rule is the same. The green one is high exposure to drought, and the white one is very low exposure. So in terms of risk, of course, in terms of exposure, in terms of exposure, yeah, the Southern Africa region is low, except the coastal area on this Namibia and the South African side. On the west, which is a moderate one. And if you combine this, you can see drought risk is very high, mostly in this region, mostly over the eastern part of the SADC region. And compared to the rest of the globe, you see a lot of drought risk. Of course, even Europe is affected by drought in this case because of vulnerability. Now we can also look at precipitation, which is of course related with drought, and 90th percentile, the extreme precipitation in 15th percentile, more or less, is an average precipitation. The 15th percentile represents extreme low precipitation, which is mainly dry condition. So in that regard, precipitation change relative to 1981-2010 for the projection period shows an increase in greener color and a decrease in brown color. Yeah. So extreme precipitation is increasing. We have seen that the mean precipitation is decreasing over Southern Africa region, but unfortunately the extreme ones are increasing, which will not add up to the total precipitation. The total precipitation anyhow is going to be less, but what this shows is that you may receive a rainfall of the whole season, maybe in 2 days, which is not good, so that is what it means when you look at this map. The extreme precipitation is increasing, and dry period is also increasing, and all of them basically will have an impact on the overall precipitation in the region in terms of risk of drought, risk of flood. This one is an index that also measures the extreme precipitation. I have already shown you maximum 1 day precipitation that you can get within 1 day. And of course, over a period of time, let's say if you have a record from 1900 to today, every year you'll have a maximum precipitation. If you combine that data over the last 120 years, you'll get a time series of maximum daily precipitation. And this time series will have a distribution, which can be described by percentile. Percentile is basically you are going to create a distribution that shows the lowest values and the maximum values. So the 95 percentile is those components of the maximum daily precipitation with a value more than the overall climatological mean, yeah, by 95%. So clearly, this is at a different level of warming. 4 degrees centigrade, 2 degrees centigrade, 1.5 degrees centigrade. Yeah? And what you see here down here is some numbers: 37 simulation, 112 simulation, and here you see 127 simulation. So these results are from models, because we are talking about projection, by the way. We are talking about projection, and it means that you have to have a model that does the simulation. So there are many simulations, and this is a compilation of different models. We have different international institutions like NASA, like European Union have their own models. Some universities, a number of universities actually, it's not some, a number of universities have their own models, and they participate in this intercomparison project. So, when you compare, use all this information, you have more confidence in what's going to happen, because making judgment on a single model is not wise, because you have a lot of uncertainties. But if you use a number of models, that uncertainty somehow will be smoothed out, and you can gain a lot of confidence in what you see in the simulation. So basically, if you ask me which one of this is more likely to happen, it's going to happen in the event that this scenario works, is the lower, was because a lot of models are participating. You'll see a lot less uncertainty in terms of accuracy. So you can see the blue ones are weather condition. The brown colors are the dry conditions. For extreme 95th percentile, then close to mean value, and then the extreme lowest value here. The extreme lowest value is decreasing, and the extreme highest value is increasing. Highest value is decreasing. So I'll show you this later on with some picture summarizing the whole concept of this change. This one is consecutive dry days we have seen earlier, again at different level of global warming, 4 degree, 2 degree, and then 1.5 degree, and change in days. Yeah, these are days, continuous days. We have seen already. Yeah, the number of continuous dry days. For instance, here in the brown color, if you see here, it's greater than 40 days are dry. Yeah, dry days. So clearly, we are looking at for Southern Africa, the rainy days, basically at 4 degree global warming level. The continuous dry days is going to increase. The extreme continuous dry days is going to increase. The mean is going to increase as well, the mean number of dry days. And then the lowest continuous number of days is going to also increase at this level. But if you go further to 1.5, the impact of global warming is going to decrease. You know, as you move from 1.5 to 4, is going to be severe. This is lowest impact, medium impact, and severe impact at the top. Yeah, and you can clearly see the impact is more or less similar globally when you move from 1.5 to 4 degrees centigrade. So the impact is similar. The degree of change is different from one place to the other. That's why you see spatial variation. But as far as moving from 1.5 to 4 degrees centigrade is concerned, you can clearly see a clear message. This is not what happened actually. This is a projection, and by doing so, you get a confidence in what is going to happen if you move from 1.5. What's going to happen relatively to 4 degrees centigrade? So 4 degrees centigrade is worse than 1.5. 2 degrees centigrade is worse than 1.5. So that's why you have to look at that's a big picture when we talk about climate change. Mean annual evapotranspiration again is going to be affected, and again here it is in percentage relative to the base period 1981 to 2010, and greener means decrease in annual mean evapotranspiration compared to the historical period. Brown color means an increase in precipitation in the future and mean annual evapotranspiration in the future compared to the historical period of 1981 to 2010. Again, global warming level of 1.5 is better than obviously 2, much better than 4 degrees centigrade everywhere, as you can see, as the situation gets worse as you move from 1.5 to 4 degrees centigrade, whether it is for the extreme mean annual evapotranspiration or for the mean evapotranspiration or for the lowest mean evapotranspiration. The situation is going to change towards the worst direction. This is projected change in river flooding according to SSP 126, SSP 245, SSP 58.5. Yeah, and the color bar down here from blue to red shows you return period. So if you move toward this blue color, you expect increasing flood frequency. Frequency of flooding is going to increase, if you move toward this more red color, you should expect decrease in flood frequency. So that means those shaded with red color is likely to occur once in every 1,000 years, for instance. If you are at this end blue, extreme blue, you expect that flooding could happen every year or every 2 years, because this extreme blue is 5 years. Yeah, so at least you'll get one every 5 years. Based on this terminology, understanding of the color bar, if you look at the Southern Africa region, scenario SP1 to 6 is a good one. Because its color is more like white, yeah. And if you move to SP 2.45, you see there is something around the eastern coastal areas of the SADC region. So you get more number of flood events, at least every 25 to 50 years. If you move further down here, this is extreme warming situation. The situation is more or less the same. You're expecting to get flood events at least every 5 to 25 years. Every 5 to 25 years. That's how you are going to interpret this figure here. So global warming, because 2.6 will cause less warming compared to 4.5, compared to 8.5. So as you move from here to 8.5, you should expect more severe cases of flooding. Yeah, this is just a comparison of global and regional potential exposure of the population to flooding, and you can see that Europe is, you can see this, the square is SSP5, square shape bar, and then if you see a white circle, it is constant population scenario, and if you see the triangle, it is constant population under CMIP6. So we are comparing the old scenario, CMIP5, with CMIP6 scenario. And in terms of exposure, clearly Africa stands out from the rest of the globe. You see, so sorry, I'm getting a call. Cannot switch off. This is a landline. I hope you'll understand. So Africa stands out very clearly, very vulnerable to flooding. You can see with a shade, dark shade in the color in the bar. It's a historical one, but the rest in color from orange to red is under global warming 1.5, 2 degrees centigrade, 3 degrees centigrade, and 4 degrees centigrade. So as temperature increases, the exposure is increasing basically under different scenarios. Asia is the next vulnerable continent. Australasia is modest actually. Central and Southern America actually, you can see exposure goes with poverty. Southern America is mostly poor Mexicans and so on, and they are vulnerable and exposed to extreme flooding. So North America is America, basically Europe is better even than Americans in terms of exposure. Is very low. It's very low because they have very good infrastructure to prevent flooding compared to Americans. Yeah. So it goes with economy. American economy is strong, but Europe are more social, has invested a lot in infrastructure as compared to America. That's why you see this kind of difference in terms of exposure to flooding. Here in this slide, again, we are still talking about impact of climate change on the hydrological cycle. So we are looking at terrestrial water storage is affected by climate change because basically climate change will lead to droughts and flooding and so on. So that's what you see. It's basically percent of global land area affected by droughts and also the population. So you see area under drought and population affected. So you can see different color here, dark brown and light brown here. Light brown is moderately severe drought case, and dark brown extreme to exceptionally severe drought cases. And you can see the land area for both of them, for both category of droughts. There is an increase in land area impacted by the global land area impacted by both of these drought. As you can see, from 2006 to 2099, you clearly see that there is an increase. The dark lines. The brown color shows you uncertainty. It can go anywhere between the bottom to top here. So there is a lot of also uncertainty because we are doing a projection. When you look at the historical observational period, the uncertainty is low. The uncertainty low, but for the projection, models are giving different results, and there is widespread projection between models. As a result, you can see there is the prediction is somewhere here and overall by this dark line, but it can go anywhere from here to here if you look at individual models. When you look at the population exposed to extreme to exceptional drought is also increasing. The rate at which this increase is more than the exposure of population to moderate to severe drought here at the top. If you look at this graph here, you can clearly see more land area means more people are affected, basically. That obviously we are not looking at urban centers where a lot of people are located. We are basically looking at the rural areas where the livelihood depends on agriculture. So that's why you can clearly see a parallel, a direct association between percentage of global land affected and percentage of population affected under both these two extreme cases of drought. Now, that is more or less the impact, but just to put into context what we have discussed, I want to really relate this slide with what we have discussed so far. Yeah, we have discussed impact of climate change on different components of the climate system, from biosphere, hydrosphere, atmosphere, land surface, the cryosphere, yeah, and human systems. These are the sectors where we have looked at the impact of climate change, even if we have focused towards the for the last hour on only hydrology. Now, in all these changes and impacts, the critical ones are temperature and precipitation. These are critical parameters. So I want you to understand how this situation is changing under climate change. So if you look at panel A, the definition of this is probability of occurrence of temperature. It's a probability distribution of temperature. In the middle is an average temperature. If you move on this side, a low temperature. Temperature is increasing. If you look at the horizontal axis, temperature is increasing from cold to hot. Yeah. If you plot all the data, here we have shown this just a line here, a kind of Gaussian shape or normal curve. You see a normal distribution for the temperature. So on the other end of the normal temperature distribution is you have a cold temperature, low temperature, and hot temperature. So normally you have cold temperature or extreme temperature towards this end, and you have also cold, hot, extreme temperature when you approach this side. This is just under normal circumstances, because even in the historical time, even before industrial period, we always have cold extreme and hot extreme temperature. But what climate change does to this temperature distribution under A is what you see under B here, panel B here. Under panel B, climate change is affecting so many things. You can clearly see this curve here, which was what you see under A. This light curve is moving towards the right, as shown by this arrow. So it moved to this direction, and you can see that now the location of extreme cold has moved towards warmer temperature. You can see from here to here. Basically, what it does is global warming or climate change is causing less cold weather. What else it's doing? It's changing. You know, the mean was here. The mean temperature, the normal temperature we experience every day, is somewhere in the middle, right? Somewhere in the middle. So this one, which is shown by the peak of the curve here under A, this peak has moved to another peak. So the location of this peak was here before climate change. Now it's moving towards the right, towards warmer temperature. So basically, climate change is affecting temperature in such a way that you have less cold temperature, you have warmer than normal regular temperature. The regular temperature itself is warmer than the old normals. So the new normals is moving towards the warm side. And now, as you can see, this side, which is hot under panel A, is also moving beyond the hot here, is moving towards more record hot, shown by red color here. The previous hot is now shown by rather kind of pink color here. So what the climate change is causing is a number of things: less cold weather, normal temperature changing to more warm temperature, as shown by the peak shift, and then the extreme heat temperature become more extreme, and also you are getting more hot weather than when there is no climate change. So you have more hot weather. Frequency of more hot weather is increasing under climate change, and also more extreme record heat is increasing under climate change. So that is what happens in all of the discussion we have looked in the previous slides. As far as temperature change is concerned, is a combination of all of this. So you can describe this extreme temperature through different indexes. That I'm going to talk about. For instance, heat waves is a way to describe some of the record heat temperature, hot temperature. When it comes to precipitation, usually precipitation distribution is, as we see under this panel here, A, the bottom panel. The bottom panel precipitation, you get light temperature, light precipitation, low precipitation is occurring. The probability of occurrence is very high, so the distribution has a maximum. At this point, it's not like the Gaussian distribution for the temperature. For precipitation, always the low precipitation is more number of days have very low precipitation as compared to few days with heavy precipitation. So the distribution looks like this. Probability of getting, under normal circumstances, probably getting low precipitation is high as compared to probability getting heavy precipitation. So under climate change, this panel you see under A, the bottom panel you see under A, is going to change in a way that looks like what you see exactly on the right side. The precipitation is going to shift, as you can see, from here to this here, less number of days with low precipitation, more number of days with less precipitation. You can see a shift in this direction from here, from dark, from light shade line to dark line. So it's decreasing. And then on the other hand, you are going to get more number of probability of getting more heavy precipitation is increased. So there is a shift in the vertical direction in terms of distribution of the rainfall. So more probable to have heavy precipitation, the probability of having low precipitation is less. So that's how temperature, climate change affects rainfall. And even if you look at the mean and the average, now the mean has also increased. We can say here it has increased, or in some cases you could say this is just one example. Actually, it's just one scenario. The location can also be reversed when it comes to precipitation. It depends on the location. So you can see the mean has also changed. So basically what it means is climate change will affect the tail of the distribution, of the temperature and rainfall. The tail means the beginning and the end of this distribution. The light end and the heavy end will come to precipitation. The cold end, the hot end of the distribution. So the tails of the distribution are very much affected. On top of that, the average, the mean, the normal temperature and the normal precipitation is all going to be affected. So climate change is going to affect in three directions: lower extreme and higher extreme, and also the mean. So basically, what it means is that climate change is not just showing in terms of trends of mean precipitation or mean temperature or average temperature or average precipitation. Is going to affect also the extreme. So we have to have extreme parameters that describe this change in under the tail of the distribution, under the cold tail and hot tails. and under the light and heavy tails of the rainfall distribution should be expressed in some ways. So I think tomorrow we are going to discuss this in detail about how we describe change in these extremes toward this lower tail and highest tail of the rainfall and temperature distribution. So I think I would like to stop here and maybe allow you to ask me questions if you have any questions. Yeah, because if you have a move, I'm not going to finish, but I'll just give you a brief introduction on climate extremes, how they arise. But later on, tomorrow, we are going to discuss in detail some examples of extreme could be dry condition, extreme dry condition, extreme wet condition, and there are different indexes that are used to describe this change in the extreme index of the rainfall and temperature distribution. So I encourage you to ask me questions so that we are on the same page. Thank you. Yeah, I think feel free to ask. I mean, here there's no stupid questions. You can ask me. We can talk about it. Because I don't know your level, I try to keep it more generic. I'm from physics background. Would love to show some questions because it helps me a lot to explain. But still, I should be able to explain some of your questions that you may have regarding what we talked. Any question? I don't. Feel free to ask questions. I encourage. I like questions. If you are silent, that means I'm worried. I'm worried that you may not get my message. Huh? Maybe talking. Yes. Go ahead.
Hello, Prof. Can you hear me?
Yes, I can hear you.
Okay. Thank you for your captivating presentation. I'll just open the floor for questions. I'll just be conducting this session now. So, any questions in the room? Okay, you can go ahead, Faith. No, I think you can talk.
No, thank you very much. Can you confirm you can hear me?
Yeah, definitely I can hear you.
Thank you very much, Prof. Mengistu, for the all the science and the graphs and the data, and sometimes it kind of helps to have a visual sort of representation of what the changes in the different parameters actually could turn out to be, even though we're looking at projections. That was quite insightful. So I've got two questions though. The first one is how often are some of these how often do you scientists actually ground truth these projections? Because sometimes you see that some of the trends that were projected from as far back as maybe the early 2010 to 2012, and they still continue on that same sort of trajectory. But do scientists actually go to the ground and ground truth and confirm that this is what they had sort of projected and that's what's happening? And in the same vein, I also want to check how interventions or these mega trends that happen actually influence this projection. For example, for the COVID-19, where the globe was literally like closed. And so that meant there was a reduction in the carbon emissions. So I'm sure that would have had a dent on either, I'm not sure if it's immediate or future direction, that the graphs are taking. Here we're also talking about the global recession and the issues of inflation. That obviously affects the business or economic side of things. And I'm sure that also has implications on emission of greenhouse gases. So how often do we get to recalibrate or to ground truth these projections and the models? And also because often after such presentations, I'm often depressed because then it's like, it's all doom and gloom, like we're heading ourselves to death, and with no acknowledgement of at least the small, like cumulative sort of effects or impacts that we're making at a small scale. So yeah, I just have to lay myself there. I get depressed usually after some of these engagements. And I don't know if I should go to the second question or you want to respond to the first one.
Yeah, you can go ahead. And
so the second one is a practical question also relating maybe to policymakers, informing decision making. When it refers to the water balance, the slides that you showed about the water balance, one of the effects or one of the impacts of climate change, at least for the global south or here within Southern Africa, is water scarcity. So, and I think that manifesting through like droughts, more frequent droughts. And the one that really hits home for me is the drought in the Western Cape. This was the multi-year drought from 2017 to 2019. And there was a lot of talk about desalination of seawater so that it could be potable water. So what effect do those initiatives, like replicated at scale, have on the water balance? Or does it negatively or positively affect the water balance? Is it something that you recommend, say, to policymakers to actually replicate at scale? Thank you very much.
Okay, thank you. I think, shall I respond, coordinator?
Yes, you can go ahead and respond to these two questions.
Yeah, I think, yeah, let me start with what you say, gloomy picture and end of this kind of discussion. Yeah, definitely. Yeah, I want people to be alert. That's what happened even in my normal undergrad class, because yeah, climate change is not something you really feel it. It's not like a pain you feel immediately. So you have to really narrate in a way that people are really motivated to start thinking about it. Not get depressed, but start thinking about it and try to understand how everyone is contributing to climate change. When it comes to projections are projection. It's a scenario. It's what if scenario. It's what if scenario, and what if scenario is not arbitrary, of course. You look at the range of possibilities and you agree with each other, because this is an international coordinated projection. You agree with each other, and let's put this 4 scenarios, let's say 4 or 5 scenarios. And if you follow this trajectory, this is what's going to happen. If you follow this trajectory, this is what's going to happen. How confident about it? Let's say the fact that we may not even follow any of those trajectory is a possibility. Actually, it's a possibility. There is high probability that we'll be somewhere in between those trajectories. But the fact that this gives us a direction is good, because we will prepare ourselves in such a way that we develop some certain mechanism of adaptation and mitigation options. Could be technological, could be, let's say, growing crops or cultivars that are drought resistance, and including the issues that you mentioned about desalination of seawater. So the models have their own uncertainty. I'll talk about them tomorrow. There are so many uncertainties that goes into the models. The way to, because it's not a truth, projection is not a truth, it's as if scenario. Now let me focus on the historical modeling, the simulation for the historical period. The performance of the models, the good skill of the models can be judged if you compare, as we said, with ground truth. Ground truth is only available for the historical period. You are not yet there for the future, so there is no way to do any ground truth in that regard. That's why you have to do scenario. So if you know exactly the trajectory that we are going to do, then you could make a forecast. Scenario projection is different from forecast. Forecast is we are expecting the current situation is going to evolve in the future, and you are going to expect this kind of change, let's say in rainfall, in precipitation, evapotranspiration, soil moisture, even on availability of groundwater, and so on. So we don't have climate forecast so far because we don't know exactly how we are going to evolve in the future. It's only range of possibilities which are described by the scenarios. So the confidence in the scenario comes from the validation exercise we do for the historical period. How good are models in capturing historically observed changes in precipitation, surface runoff, evapotranspiration, and different components of the hydrological cycle? So that kind of validation has been going on. There is certain level of uncertainty because anything, when you do measurement regularly, in any measurement, not only climate, even if you go to chemistry laboratory, do some measurement, or a biology laboratory, do some laboratory measurement, you will have uncertainties coming from different sources. In the same way, we have uncertainty in models, even for the historical period. So in the past, if you look at the evolution of models from 1916s, because modeling started actually only in the 1916s, once we understand there is climate change. If you look at the improvement in climate skill from 1960 up to now, there is a lot of changes because every year, every day, we understand what goes wrong through comparing with the ground truth. So that comparison allows us to modify our models, adapt our models. So there are still uncertainty that exists in the models, but the accuracy has dramatically improved over periods. So the current models are not perfect. They differ from each other. There are good models. There are extremely low-performing models. But if you look at the mean, the model improvement along the timeline from 1960 up to now has shown dramatic change. But still they have uncertainty, which is comparable to actually observational uncertainty. So I would say that the models are good, but doesn't mean they are error-free. They have errors because of the assumption we made when we make the modeling for hydrology. We have different components, and the mathematical representation of the different components in the model involves a lot of physics, a lot of chemistry, a lot of biology, a lot of fluid dynamics. And those equations that you get on the papers will not go to the computer as it is. It goes to the computer through some kind of approximation. We call it numerical approximation. So there are errors. They are not perfect, but the performance has evolved very much in recent days. The last one is about the desalination effect to get fresh water from saline water. Yeah, this, the problem with desalination, of course, has an issue on a larger scale, but we don't have a technology to the extent that because of desalination of the seawater will impact the oceanic circulation. Oceanic circulation is governed by difference in density and salinity is very critical for smooth functioning of the climate system. But the small activities related with desalination currently going on globally will not affect anything. In fact, as far as the whole water balance is concerned, you are moving water from one component to the other. Water is not going anywhere, by the way. Yeah, water is still conserved. Water is conserved, but it exists in the form of, let's say, if you are using water for agriculture, it exists in the form of biomass. Yeah, but that biomass will be converted back to the water actually later on. You are going to consume it, and then you are going to have different products and so on. So it's not destroyed as far as the water. So, but the fact that it's moving from one component to the other is going to affect certain processes. So desalination is not a problem, but the problem is it's a very costly business, and as far as I know, only very few countries in the Middle East are using desalination techniques. Yeah, that is it. Did I answer all your question? Okay.
Yeah. There's also another question in the room.
Yeah.
Mr. Katambo, go ahead.
Yes, good afternoon, Prof. Thank you for the wonderful presentation. There is a point that you mentioned in one of the slides concerning the uncertainty of the models. So you said, I'll paraphrase it, if we use many models, we can reduce the uncertainty of the models. So I would like to find out how you use the many models. Is it comparing from one model to another, or as an ensemble of models, ensemble models? So is it comparing with a multi-ensemble model, or perhaps from one model to another model, and so on and so forth?
Yeah, actually, you answered your own question. Basically, that is the answer. When you use models, they give different results. Some underestimates, some overestimates, some are even closer to what is observed. So if you average them in the sense of ensemble mean, then you get something which is much closer to the observation. So taking the mean of all models will remove some of the scatter in the data. So always the ensemble or the mean of the several models, which you call it ensemble mean, is performing very well. So the tradition is that modelers are doing a lot of efforts to improve the models, and no models are perfect, because no models are better than the others actually. Yeah, they have sophisticated physics, sophisticated chemistry modules, sophisticated radiation modules, but they may be off in certain direction, while others are simplified models, but the result may be a lot of underestimation, a lot of overestimation, and so on. So if you average them, you can get rid of the mean. It's not really something you recommend from physical point of view. This comes from just observation, and the fact that when you average different observation, actually you reduce uncertainties, the scatter in the data. So you are not comparing individual models with each other. It's difficult to compare models with each other because of the different assumptions made in each of them. And there's no, the only way to compare models with each other is to compare with observation. Observation is a reference. You compare one model with observation, you compare the other with the same observation, and you can say that this model is performing better than the other. But if you average all of them and compare to observation, the mean is which performs very well, because the scatter in the data will be removed through averaging. A simple concept: you add different number, divide by the total number of the models, you get better result. That's what I mean. Yeah. Okay. Go ahead.
Yeah, go ahead, Mr. Rande.
I think mine is just a follow-up from what Mr. Gatambo just asked. In my study, I'm considering to average about 5 of them. So I'm just trying to find out what could be the recommendation. Is it possible? Is 5 enough, or should I go more?
Yeah, interesting question. Actually, yeah, 5 is better than 1. If you add more, you get better results. That's the whole term of rules, and there is no limit in terms of the number of models. But as far as you involve more than 1 model, depending on your case, you can argue that you are using the ensemble, yeah, and it's performing better than the individual models, yeah. So 5 is still okay. But if you have access and the infrastructure to do the analysis, if you add more models, then you can confidently talk about the performance in that direction. And nowadays, people are talking about in literature anywhere between 10 to 30, 40 models as part of their ensemble mean.
Yeah, thank you. I have a follow-up on this question here.
Mm-hmm.
If you add more models, it means you are approximating reality. What are the negatives? Because I assume there might be any, like maybe on the sensitivity. We have to be worried if you continue adding more models to average.
Yeah, well, of course, you don't add different categories of model together. You have to make sure that the models are, at least for instance, we have atmospheric only models. We have, let's say, coupled models, ocean coupled models, and there are different assumptions. Even the resolution of the models are also important. You know, when you choose your models, you have to look at all these criteria. And you cannot, for instance, average couple models with models, atmospheric only models prescribed by, let's say, sea surface temperature. So when you get your ensemble mean, make sure that they are in the same category, make sure that they have this, similar resolution, and also, of course, temporal coverage. So don't take it that you can add as much models as possible without any limitation. Is not what I mean. You have to first select what category of models you are working with, and then think of the resolution, because the resolution itself has an impact on their capability to resolve the detailed physical processes on the ground. Yeah, thank you.
There was also another question in the room. Mauricio, go ahead.
I have one comment first, and after I have one question. I sorry for my idea. Sometimes I look at global warming like something like a big business, where behind the global warming there are a lot of some political and economical issues from the big nations, because there are a big tendency when the people talk about the global warming to see only and explain the change, the climate change, only because of the anthropogenic activities. And sometimes the comparisons from the temperatures and the other variable that can provoke range or change in the climatic change. The people or the scientists did the comparison like with the last 100 years. And 100 years in historical of the health is almost nothing, because the historical have the health have a good time of the a geological time. And I think that we can not only see the anthropogenic activities without the natural cause, because the sun is the most source of the hot in the health. Almost 19.9 of hot come from in the sun. And sun every 11 years, during 11 years, in the sun have periods with high intensity of hot, and have other times, other periods with low intensity. In this, it's normal in the period with high intensity of hot, the temperature in the health is increasing. It's normal. And in other period, it is normal that the temperature reduce. But my question is, why when we are talking about the climate change, I can see, for example, in the screen, for example, when we talk about the temperature, we look only when the temperature increase. Why not? We can see in the two perspectives. Increase and the other period can be decreasing. And the other things, I look when I look the story of the health, I can understand that the health was 4 kinds of atmosphere: primitive atmosphere, atmosphere reductor or reduced, atmosphere proper for living being, and actual atmosphere. In this atmosphere, in the first atmosphere, for example, have a lot of dioxide carbon in the atmosphere, and the oxygen doesn't exist because the oxygen reacted with hydrogen to create water. But in this atmosphere nowadays, have a lot of we have in this atmosphere. We have a lot. We have in this atmosphere is oxidative. Every 21% of oxygen. My question is, how we can talk if we compare these two atmospheres, the primitive atmosphere and the now actual atmosphere, we can see in this atmosphere there's a lot of oxygen comparatively or dioxide carbon. How we can talk about the global warming in these times? Is my contribution, so I'm sorry for my English from you.
No, this is okay. I understand what you said, and it's very clear enough for everybody. I think I haven't included in this presentation because of the scope of this module. But as we said, there is climate change, natural climate change, particularly if you look at geological time scale, yeah? Geological time scale, if you look at the last 800,000 years and 1 million years and so on, if you look at the primitive atmosphere, how it evolves, yeah? From Big Bang, big explosion to current situation. So even when you look at them, the geological time scale climate variability is explained by different geological processes. Yeah, even land formation is taking place at the same time. As we said, early atmosphere composition was not the same as current composition of the atmosphere. It has evolved over time. And if you look at the climate, you can look at the current climate as far back as 800,000 years. And the climate change is happening. The Earth is fluctuating between extreme cold, extreme warm temperature. During the Little Ice Age, for instance, there was the whole Europe was covered by ice, and the ice coverage even covers some part of Africa, So those are basically mainly natural, actually, mainly natural. I'm talking about what happens 120,000 years ago, Little Ice Age period. Yeah. But if you look at the fluctuation, it's mainly happening because of the solar cycle, the orbital variation, not solar cycle, orbital variation. So, for instance, when glacial period appears, most of the carbon dioxide in its atmosphere is buried under the ice. So CO2 in the atmosphere is very low. And the ice will change the albedo of the edges, and as a result, the cooling is actually amplified during glacial period. When that cycle ends and we start entering the interglacial period, now the ice that is covering most of the globe start melting, releasing some of the carbon dioxide. So basically, the carbon dioxide fluctuation in the atmosphere is not because there is additional production of carbon dioxide in the atmosphere or greenhouse gas in the atmosphere. It's because of the fact that CO2 is removed from the atmosphere and buried under the ice during glacial period and released back to the atmosphere during interglacial period. So comparing this with the current climate, the current historical, what we call it, super interglacial period, they are totally different because we are adding externally additional CO2. In the past, even if you look at historical geological time scale, the fluctuation is fluctuation of existing CO2 being removed from the atmosphere, buried under the ice, and released back to the atmosphere because of warming. But the current ones we are adding extra CO2. That is not needed for global warming. I know some of the people who argue that there is no climate change. This is just part of the natural climate cycle. Uses actually exactly the same argument that you are using. But this is dangerous because there are many evidences that indicate that the current global warming is not part of the natural cycle. You can look at radiation released, captured by the atmosphere through the atmospheric window side, and you can look at the amount of oxygen available in the atmosphere. Look at oxygen. Yeah, oxygen in general is around 21%, but you can make a measurement and you see a fluctuation of oxygen because of biomass burning, because biomass will not take without oxygen. So there are so many other evidence. In fact, I may even share some slides tomorrow. I don't have it now, which shows that there are different line of argument that clearly shows the current climate change is different from the historical climate change, natural climate change that happens over a geological time scale. Yeah, that's what I can say. Yeah.
Any questions online? Participants online, any questions?
I don't see any questions listed, Mr. Tafila.
Okay.
I'm checking the online ones. I do not see any inputs from the online participants.
So can I get email of the students so that maybe I can share tonight some of the posters, or should I just do through Nore?
Yes, you could forward to Ronelle and she will also circulate widely, but either way we'll also forward the student group email so that if you have need for any further interaction, you can freely do so. But you can forward to Ronelle and we will in the reply also copy in the student group email. I'm sure they'll also appreciate having access to engage with you on the topic. So we'll also share your email contacts with students.
Yeah, no problem.
Yeah, I'm going to actually paste it in now. I'm very forgetful. So let me copy in the student email group email into the chat. Okay, yes, and I'll also copy yours, Prof, into the chat so that they also have your email address.
All right.
Great, but thank you so much. Thank you so much for this insightful. It's been a long 3.5 hours of you talking, so I know how that can also be straining on you, Prof. Thank you for making the time, for sharing your knowledge and engaging with our doctoral fellows on the questions that probably might be quite pressing, and it just helps to have a conversation and dialogue around some of these topical issues. We are looking forward to further engaging with you and the rest of the team. And for purposes of our students, Professor Tsidu is actually the coordinator for this block of seminars. So he's the one who has identified other experts and put them together and structured the whole the 1 week training. So we quite appreciate the work we're doing behind the scenes, Prof. And we are looking forward to what is coming before us during the rest of this week. Thank you so much.
Okay, thank you so much. No problem. It's my pleasure.
Yeah. Okay, colleagues. Same link, same time tomorrow. Have a good afternoon. For those that are joining the Climate Forum, we are looking forward to engaging with you on that platform. I think sessions will be resuming at 2 for the Climate Forum. The opening just ended an hour ago, but the technical sessions will continue. So you have a good and productive afternoon. Goodbye.
Okay, thank you. Bye.
So you can't.
So it's probably running.
Yeah.
She's the one who started.
Ronel, can you stop recording?
You need to eat now. He wants to take away the things.
Yeah. You can leave.